So let's recap from the last video. We saw this. The washer method, right here, the washer method comes from having the volume of the hole minus the volume of the hole in the middle, right? We factor our pi out front because it's common to both terms. We call the outer radius, or the longer, bigger radius, big R. The inner radius, the radius of the disk that is the hole in the middle, we're going to call that little r. So that's what all those variables represent. So the washer method itself, we find the volume of revolution of this three-dimensional solid by taking an area in the plane and swinging it around either a horizontal or vertical line by pi times the integral from a up to b of big R squared minus little r squared. If we are revolving around a horizontal line, just like our disk method, then our thicknesses are going to be with respect to x. If we are revolving around a vertical line, we are going to have thicknesses with respect to y. Now, you don't need to memorize this formula. I want you to internalize this formula from drawing yourself a good picture, recognizing from your good picture that you're going to have a hole in the middle, and therefore you're going to need to use the washer method versus the disk method. With the hole in the middle, recognizing you're going to have little r, recognizing you're going to have big R. So no need whatsoever to memorize this formula, so don't even be tempted to do it. Okay, let's use the same region in the plane, and now we're going to revolve this same region in the plane about the y-axis, and we're going to find the volume of that revolution. So let's go back over here. And let me find, I'll try again. This is very hard to do using the airliner. Hey, that's not too terribly bad. And then the parabola will reflect, oops, getting off center there. The parabola will reflect something looking like that. So that's not bad. Okay, now we're doing things though with respect to the y-axis. We are spinning about the y-axis. We're taking this region, this area, and we're just taking that whole thing and spinning it about the y-axis. So let's draw one representational cross-section somewhere along in here. I'm going to go from the parabola to the parabola. That's going to give me the whole thing, the whole volume. It's going to have thickness. We are revolving about a vertical line. Our thicknesses are with respect to y. So that tells us right there we are going to have to integrate with respect to y. Here, from the y-axis all the way up here to the parabola is big R. Okay? I'm going to find a different color. We'll go to blue. And now from the line, if I take that point and swing it about the y-axis from the line to the line, we begin to see our washer emerge. Okay, so we have a hole in the middle, and the distance from the y-axis to the line now is our little r. Okay, so let's go back and let's remember we have pi integration from a up to b of big R squared minus little r squared quantity times our thicknesses, which means the dual role that this plays tells us that inside of this definite integral, everything must be with respect to y. Not just big R and little r, but a and b must also be y values. So let's start finding the pieces of what we need here. And so right ear on right shoulder, the upper bounding curve, which is where big R comes from, is the parabola. So big R is going to come from this function. Right ear on right shoulder, the inner bounding curve, or the lower bounding curve according to the y-axis, this distance all the way up and down here, which is going to be little r, is the area or the region in the plane between the y-axis and the line. So this is little r. So let's start filling things in here. We'll worry about our limits of integration after we find little r and big R. Now again, everything has to be in terms of y. So if big R is y equals x squared, I need to get x in terms of y. Everything has to be in terms of y. I'm integrating with respect to y. So I'm going to take the square root of both sides. So x would have to be the square roots of y. So there's big R. Big R is the square roots of y. Right here on right shoulder, you can see that big R for the y-axis is indeed a square root graph, right? Now let's look at little r. Little r comes from the line y equals 2x. I need x in terms of y, so I'm going to divide both sides by 2, so x is 1/2 y. So little r is the line 1/2 y. And right here on right shoulder, if you'll look and see, this is a line, according to y, with a relatively shallow slope. It's definitely not a slope of 1, right? There's y equals 1, there's x equals 1. That's what a slope of 1 would look like. So we're right on the money. Even intuitively, that makes sense for us. So we have big R squared minus little r squared times our thickness. Now the only thing remaining for us to find are our a value and our b value. Well, just like we found intersection points before in terms of x, now we're going to find intersection points because that's the same. Whatever this y value is, whatever this y value is, we can't always count on it being the value that shows up on the axis. We can't just eyeball it. We have to do the mathematics to make for sure that we're right about that. So once again, our limits of integration are going to come from the intersection point. So let's square both sides. We get y equals 1/4 y squared. I'll work in this direction. Now remember, we are definitely going to have to use good algebra, ladies and gentlemen. Don't divide both sides by y and all that kind of stuff. Use good algebra. This is a quadratic function. I am going to multiply through by 4, though. That's not going to hurt a thing for me to do that. And that gets rid of that fraction for me. I'm going to factor a y out. And it's very easy to see from this point that my intersection points are 0 and 4. So here's my integral, and I'm integrating according to y from 0 to 4. So I'm going to get rid of some of this work here to give us some room to evaluate this definite integral. So now we want to find the volume. Here is the volume. It is pi times the integral from 0 to 4 of the square roots of y squared, so that's y, minus 1/2 y quantity squared, so that's minus 1/4 y squared dy. Please don't forget your pi. We'll talk about the most common mistakes made in this setting when we get through with our examples, but one of them obviously is dropping the pi out in front. So antiderivative, 1/2 y squared minus 1/4 times 1/3 or 1/12 y cubed, and we are integrating from y values of 0 to 4. So we have pi times 1/2 4 squared minus 1/12 4 cubed, and then minus, we only have y's. It's not the quantity y plus or minus anything. It's just y. So when I plug 0 into both of those terms do indeed go to 0. Actually, right here, if you've listened to me all last fall, we're done. If this is a free response question, walk away from this problem right here. That is a perfectly well-defined, beautiful, real number value. You don't have to clean it up. hopefully with this second example, especially with respect to y, you get the idea and get a better feel for the washer method. Again, the step-by-step process that we got from the disk method was to draw a picture. And you'll be able to see in the next example that I work that draw a picture is very important. One thing that I would add to your process now is to draw a picture and find big R and little r. We need to find both big R and little r for the washer method. And then we want to identify or find your integrand, right? Write your integral. Your integrand is this part of it right here. Get that written. The third step was to find your limits of integration. And then the fourth step was to integrate, or actually find the volume. Okay, so let's move on and start our next example. So we have the same region. I know all three of these examples use the same region in the plane, but I want you to see that we can spin around any horizontal or vertical line, the x-axis, the y-axis. Here is a vertical line in the plane. It's the vertical line x equal 2. So here's the vertical line x equal 2, and we're taking this region, if you can see it here, and we are, let's say we anchored this point and we were able to pick up this area and just spin it right around this vertical line x equals 2, we're going to have a three-dimensional solid that's going to look something like this, right? Here is the center of this very bottom cylinder here. We could draw another cylinder here. Here's the center of it. The distance from the center to the outermost function is big R, and the distance from the center to the innermost function there would be little r. So hopefully you get an idea of what the three-dimensional solid would look like. Here, one cross section has already been drawn for us. I'll put some thickness on it so we can see that we're dealing with a washer and not just concentric circles there. So here's what it looks like. This, when we get away from spinning around an axis, when we're not spinning around the y-axis or the x-axis, big R and little r can get a little tricky. All right, so the outer radius, the bigger radius, the longer distance from the center of our washer to the edge, we're always going to call big R, and then the smaller one we'll always call little r. So the outer radius is big R, the inner radius is r. So let's go about seeing if we can figure out what those are. I'm going to clear some of my drawing away here. Maybe we can see things a little better. Now, we are spinning around a vertical line. When we are spinning around a vertical line, our thicknesses are with respect to y. When we talk about a region in the plane, here is our axis. When I talk about the line x equals 1/2 y, I'm talking about, if I talk about the area trapped in between this line and its axis, here's the area I'm talking about. So if I want to take that, if I want to take x equals 1/2 y and I want to swing that around a vertical axis, then this is the region. If I just write that, this is the region that I'm talking about. And you can clearly see that's not the region that's being swung. It's this region right here. Here's the region that's being swung. So be very careful about how you find little r and big R when you're swinging around a non-axis line. I'm going to stop right here. We'll pick up this in the next and final video, so look for that.